So tonight, I'm hoping to convince you all to start thinking about changing your perspective when doing data science from batch operations into real-time operations. And hopefully I can make a convincing argument to that effect as we go through. This is a statistic that never ceases to surprise me, but I'm wondering if it should not be surprising. VentureBeat recently published this 87% of data science projects never make it to production. So might as well take a quick sample here. How many in this room have had a data science project make it to production? Okay, that looks like about 13%. How about this? How many people have had a data science project that they've finished, but it didn't go to production? Okay, I mean, that almost looks like 100%. So perhaps I shouldn't be surprised. But it is a little shocking given the rise of our industry and, the quotes, data is the new oil, right? Data scientist is the sexiest job of the 21st century. This number doesn't seem like it should be right. Now, there's a lot of reasons that people give for why this can happen. The panel that VentureBeat was quoting was made up of people from Gap, IBM, Microsoft, Google, and they talk about things like data silos, the lack of collaboration. But the one that I'm going to focus on tonight is this idea of commercial culture, right? So everyone thinks that data is the new oil, but they don't know how to correctly employ us as data scientists to get these products to production, right? And if you guys come out to Yard House tonight, I will happily share the tea on all of the crazy things in my career, from being in the intelligence community and TNS to Cortex to Cobrain. Probably some of you guys know those companies. I will happily share all of the sordid details of why things didn't make it to production or didn't make it to production. But I feel pretty strongly that we are being employed incorrectly as data scientists, and companies know how to leverage software engineering teams, but not necessarily how to leverage their data science teams. So we think that there might be a solution, right? We as a community need to figure out how we increase our effectiveness in getting these models to production, because that's value, right? That's where the value comes from, is sort of achieving that data gap. But probably all of you feel this to your bones. We don't want to take on engineering responsibilities. Issues of security and privacy and rate limiting and DevOps, they are very important issues that aren't going to help reduce that 87% number, right? That's not what we should be doing as a team. And so I'm going to try to explore ways that we might be able to make that happen, where we're still contributing to an engineering effort, but where our focus is on the data rather than on the deployment of those systems. So let's take a look at what we do right now, or at least how we did things before. There was a pretty stark divide, right, between the model selection workflow, where we have some initial data set and we go through the feature engineering, algorithm selection, hyperparameter tuning, right? And then we have some model that we throw over the wall, right? And so there's that divide, but the idea was that we would take those models and put them into production by using ML ops, which used to be a big buzzword. I know now it's AI, and I got treated to all the Salesforce AI ads. I was walking through Atlanta this morning on my way here to DC. But ML ops used to be the big buzzword, where we're thinking about things like model management, explainable applications, monitoring, retraining, triggering, and getting feedback to our users by embedding these models inside of applications, right? And clearly that 87% number says that there is a divide, there's a gap, right? It doesn't actually go from the model selection workflow to the MLOps workflow. Why is that? So my proposal for us all is to rethink about how we engage data instead of batch training and static databases, but start thinking about things in terms of data flows, not just in the inferencing side of things, but also on the training and experimentation side of things, right? And having all change happen through a data flow and keeping our data as immutable as possible while it's moving through these data flows. That's my proposal. And I'm going to talk about, I'm going to skip ahead a little bit. I'm going to talk about three things that may help us understand how we can engage real-time data flows in order to contribute to the product efforts of our companies, or the decision outcomes, if you're not part of a commercial space, of our companies, without being involved in the training. And by rethinking things as data flows, we can end up with things like reproducible training, right? Which guarantee you is not something that we have right now. I don't know if any of you have tried to retrain or reproduce a model that you trained even 3 months ago. I know I cannot. Asynchronous online and reinforcement learning becomes more prominent and more important. And we're going to take a look at how that changes the way that we think about the algorithmic constructs. And finally, we can talk about issues of data quality, deduplication, and anomaly detection in more meaningful ways when we think about data flows, as opposed to this batch training thing. So I'll go through all of these. But I think the other big thing, just backing up for a second, is that when we rethink about things in data flows, what we get is the opportunity to unlock real-time analytics, right? And that idea of real-time analytics, that's another place of value, right? That's another source of value for the organizations that we work for. Now, real-time, that's tough. So before we go too much farther, I want to at least start talking about where the lines are with real-time. So in particular, there's two types of real-time. There's hard real-time, where there's a deadline on the computation. And once that deadline is up, it doesn't matter how far you've gotten in the computation. It's over. You can produce no value from a result on that computation. The thing that comes to mind, you probably have all seen that GIF on LinkedIn of the tomato sorters, where those little hands are flicking away the green tomatoes, right? That's an example of a hard deadline. Once that tomato goes past the sorter, it doesn't matter if you've identified what color it is using computer vision. You're not going to be able to operationalize the sorting action. So that's a hard deadline. But I propose to you, even though you might feel like most things are hard real time, actually, most things are soft real time. And soft real time doesn't have a hard deadline. It just has a decreasing value function, right? The more time that goes by, the less valuable a decision or an analytic is, but it's still valuable, right? Until enough time goes by that it actually becomes valuable again in the form of historical replay, right? And having an understanding of what happened in the system over time. Now, I'm a computer scientist, so one thing that you will hear me talk about in a computer science talk, as opposed to a data science talk, is that time is not real, right? There is only a sequence of observable events that happens, and that's also true in data science, right? So sequences of events are more real than instantaneous time. Timestamps don't matter. Just the order of things that happened, that's what matters. And there's a lot of analytical opportunity when you start to consider things in that light than in the light of batch training or decaying old data. You know, that idea of age kind of goes away a little bit, right? The sequencing, right? That is where the value is. That's where the information is. That's where the insight is. So hopefully I can convince you of that as we move through these topics. So let's start with reproducible training. Now, as scientists, right, probably all of us think that reproducibility is important, but with our engineering hats on, it is more than just peer review or the scientific method. Reproducibility is essential for explainability, right? Your model's behavior in model space is only as explainable as your features are, as the model space definition is, and how generalizable your data is. And if you can't reproduce that feature extraction process to get at that model space, you won't be able to explain any behavior. That gets us to this idea of debugging, right? One thing I say all the time is that exceptionless errors are the worst thing. And I have lots of anecdotes about how we accidentally flipped two columns. And so we were inferencing on data that didn't match what we trained on. And the model was perfectly happy to give us whatever. And it was just wrong, right? So debugging and validation, right? Understanding the risk, understanding that the uncertainty that the model embeds, you need to have reproducibility for that, right? Models are not meant to be perfect, right? If you can achieve an F1 score of 1, right, or a coefficient determination of 1, then I promise you there's a heuristic mechanism that is better at performing that computation than your model. So models aren't meant to be perfect. And so we have to be able to reproduce our models to understand the training process, the learning process, in order to do this debugging and validation. It is incredibly important. And like I said before, I guarantee you guys can't do it, right? Unless you have a really robust human-based process, you can't do it because our databases are not built for that. Generally speaking, you're using two kinds of databases, right? Transactional databases that are focused on OLTP performance, right? Those databases are meant to power applications, not analytics. As you make changes to small numbers of rows in the database, they return results very quickly, and they might be able to do aggregations and joins very quickly for you as well. But their whole purpose is to reduce duplication of data, to normalize your data to some schema, and to perform transactions in isolation as quickly as possible. And any update that you write to that kind of database is going to change your row with no history and no provenance. On the other side, you might be using an OLAP-oriented database, like a columnar database. My favorite is Cassandra. I have a very soft spot in my heart for data stacks. I really love those guys. And so if you're using Cassandra, great. You're going to get efficient aggregations and joins out of the columns that the queries that read in whole columns. And you can append records to those columns very quickly as long as you're not worried about writing whole rows to the database. However, you're not going to be able to identify easily individual rows, not without some advanced hashing function. And that's built on purpose. So quickly, you can see these databases are not oriented towards reproducibility. But what's weird is that both of these databases, Postgres and Cassandra, their entire performance comes from a log, an ordered sequence of events, right? So if you guys know about database internals, you'll know that there's a write-ahead log. The log is the database, right? Everything else is just a cache on top of the database. And so in the database community, we refer to this log as change data capture, right? Every insert, update, select goes into this log, right? And if you have access to that log, you would be able to see how your data is changing over time. Now, there's a lot of projects that have identified this opportunity recently, and there is a lot of interest in change data capture. The most prominent of those projects are something that we would refer to as event systems, right? Log-based event systems or streaming data systems. Kafka, Red Pandas, Polars are kind of at the top of that list. Ensign is another kind of database, the database that Rotational has written, that thinks about things in terms of the sequence of events. And so what happens is as writes come into this database, you have access to the log. And at any point, you can take a snapshot, right? You can take a view of everything that's happened up to that point in the log. But that also means that this question, how do you identify the instances that went into your model, becomes a much simpler problem. Because instead of having to worry about taking a snapshot, dumping out some CSV, dealing with this other data management problem altogether, instead, all you have to save is a start offset and an end offset in the log, right? And the key term here that everyone should remember is this idea of change data capture, CDC. It's a really technical computer science term, but I promise it's going to become super important to your lives as data scientists more and more as time goes on. Because not only will we start to record the history of events, we're also going to start to record the provenance of those updates. And when we start thinking about things like privacy and responding to privacy laws, California just passed the One-Click Delete Act, right? Where any in the world, if you just one click, one request, that data has to be deleted, deleted and overwritten, deleting off of, and that's the law now. And how can you do that if you don't have provenance information about where that data was sourced from? So this is going to become extremely important, not to your lives as data scientists, but also to technologists everywhere. Change data capture is going to continue to be elevated in importance. Now, most of the time, when you're using change data capture systems, you have a new idea, right? You have producers of data and consumers of data. Producers of data have to be able to write into this change data capture log as fast as possible, and consumers of this data have to be able to read off of this log as fast as possible, right? And like I said, everything in between is just a cache. It's just a view of that data. And that view can be a Cassandra database, a Postgres database, or a CSV file, but your model will have this idea of when it was trained on, not in real time, but in sequence time, right? Start offset, end offset. And it gives you that reproducibility that you wouldn't otherwise have. And if we had access to the CDCs in Postgres and Cassandra, you might be able to do this, but that's not what those things were written for. They weren't built for user access. They were built for fault tolerance and reliability. Other benefits of using a streaming log-based CDC system is that it turns out it actually makes things easier to join and to join to other data sources with read-only access, right? So many of you may have experienced getting excluded from access to the application database, right, by the DevOps team or by the database administrators because you can't be trusted with the data. Well, in a CDC log, this is immutable data, right? You can't actually hurt the data, right? So fork off that stream, and that problem that most data scientists have of where's the data? How do I get the data, right? That becomes solved. Tombstoning is also another important idea, right? Rather than deletion, delete and overwrite, you can tombstone records to preserve privacy and to preserve the idea of record removal so that the data doesn't escape the system, but so that you can still have reproducibility inside of your systems. Although we'll have to talk to some lawyers to figure out if that's within the scope of the new California law or not. And finally, your data transformation efforts will actually preserve your steps, which is kind of an interesting thought because, one thing that we said a lot as data scientists is you have to have a worm store, write once, read many. You have to have that raw data because someday you're going to want to do a data science project that is going to require that data. And if you did any destructive transformation, you can't get back to it. Well, with CDC, there is no such thing as destructive transformation. And you can get access to data at whatever point of that transformation step that you would like access to. You can also insert data into the pipeline at whatever step you want access to. So it actually frees up more and new varied data sources for your machine learning models. So clearly this is a very good thing. But we do have to change the way that we think about data to use this topic. Now, SQL is not going away because SQL can query these things, right? Obviously, if Postgres is built on top of a CDC, SQL can query these things. But we do have to change the way that we take an algorithmic approach to streaming or real-time data. And good, hopefully, that brings us to this idea of asynchronous, online, and reinforcement learning, and changing our idea of the algorithmic constructs that we're going to use to operate on this data to collect the insights that we're looking for. So here is an architecture for asynchronous inferencing, right? Just an example architecture. And this architecture also highlights the benefits of using streaming over an application or a static data store. Let's call it a static data store. So your application is here, right? There's some web application, in this case, Django, whatever, right? That's going to work with a database, and all of our users are going to interact with this thing. If you guys want to do synchronous inferencing, you would have to build some sort of microservice, right? That the Django application would have to connect to and send instances to that microservice and get a response back. That's bad, because now you are responsible for the DevOps of that microservice, rate limiting, authentication, security. Like, that's not what you want to do, right? We want to be working with data in the native way that we work with our data. Now, Django, for a long time, has had the idea of asynchronous operations, and most web development frameworks do, right? So for Python programmers, it's something like Celery. If we want to do a task that is going to take a long time, like sending an email, and we want to have 200 millisecond responses to our users, we're going to put that task in a queue, right? And we're going to wait for it to be completed before, and our users can just check in from time to time to say, like, was that task completed? Inferencing can also take a long time, but more importantly, we want to decouple it, right? We want to decouple it from the service. So here we can have a data stream, this instances topic, right? So instead of tables with streaming, we usually talk about topics, right? Which is just a table. And so the Django application can publish, right? That's that idea of publishing data as quickly as possible into the stream, into this topic. And we can have some model inferencing handler out there that can subscribe to the stream and read the inferencing requests. Now you can see that in this pull versus push methodology of operation, you don't have to worry so much about authentication, rate limiting, right? Because you can spin up as many handlers as you need. And actually, as it turns out, it becomes a lot easier to swap out models and do A/B testing and all kinds of stuff, because you just have to collect from this CDC log, right? And you can sort of start at any point and start again. In order to get the inferences back, right, you'll publish your inferences, right? And you actually don't care who's going to consume these inferences, right? Someone asked for an inference and you said, here you go, it's on this inferences topic. And we can use a sync, which is a special term for a handler that consumes from a topic and writes it into a database, right? So we can sync that to the database, and now Django has access to it once again. So we need to sort of rethink how we're doing things. We need to operate in an asynchronous modality. And again, that gives us this benefit, I mentioned before, which is you have historical replay on this topic, right? So if you want to train a different model, or you want to do an experiment, right? Would a logistic regression be better here instead of the gradient boosting that we're doing? Well, you have all this historical replay, and you will never, ever have to touch the sacred application database, right? That's a good thing. Or if you care about the inferences and you want to build a compound model, right? Well, they're your inferences, right? Just grab them off of that topic up there, right? You want to join these instances with some other instances, right? It's all completely in control because it's immutable, read-only context. But like I alluded to, we have to do better than batch, right? Because we're now in a real-time world. We're now in an asynchronous world, and there are things like microbatch, and you can certainly collect all of the instances in a topic, but you're not doing real time anymore. So how do we rethink the algorithms that we're working on? And this is where the online and reinforcement learning stuff comes into play. So here's a simple example, right? At the top here, we have a variance computation, right? This is probably the variance computation that you all know and love, right? It's just the sum of the difference of the instances minus the mean squared divided by one less than the number of instances, right? The problem with this computation is it requires batch. And why does it require batch? Because you have to know the mean in order to do this computation. At any point in that CDC log, you don't know the mean unless you replay everything to get the new mean. And then when you go one step forward, now you have to recompute the mean again. So this is not an online computation. So we have to switch the way that we're computing. This composition down here is another computation of variance and therefore standard deviation that is online, right? And so let's look at the differences. So here we have the number of instances times the sum of the square instances, less the sum of the total squared divided by n times n minus 1, right? The total number of instances. So what makes this algorithm different than the top algorithm? And the answer is state, right? What state you have to compute. And even more importantly, the fact that this computation for variance is associative, commutative, and idempotent. And generally speaking, that's what we have to do with our algorithms. We have to transform them into the most associative, most commutative, and most idempotent form in order to do the computation. The comparison here is what we have to store, right? So here we need to know the mean, but here we have all associative operations. So this little Python sample shows you, or a snippet shows you, what we have to store. First thing is we have to store n, right? So we're just incrementing n every time an event goes by, right? And that will give us n. We also have to compute the total, right? So we just keep a running total of all the instances at each point, and that gives us this sum over here that we can square easily whenever we want to compute the variance, right? And then we have to know the sum of the squares. So again, we just keep the running total of the squares of the sample. And now at any point in that log, we have enough information to compute the mean, the standard deviation, and the variance and do a distributional analysis, right? Oh, and as a bonus, we might as well also track the minimum and maximum, right? Now we have a full distribution. And you know, the point here is that we have to change the way that we think about what state we need to keep and what we're able to do in an online fashion versus something that we have to do in batch. So this is a relatively simple example, but there are certainly more complex examples. So let's give a quick definition of online machine learning. In online machine learning, data is available sequentially. Sound familiar? And at any given step, that step is used to select the best predictor for the next step, rather than iteration over the entire data set. Now, you guys have all used an online computation before, and that's naive Bayes, right? Updating a truth table is 100% an online computation because you're just adding and maybe doing a little smoothing at each step. Now, online machine learning comes from really large data sets, right? When those data sets were too large to iterate over and store in memory. And then big data came and we threw that idea away. But now that we're back to streaming data, this idea has become more important. And again, it's really a simple matter of switching your algorithm. Rather than ordinary least squares, you should be looking at recursive least squares. Rather than using stochastic gradient descent, you should be looking at incremental stochastic gradient descent. For other convex optimization, thinking about follow the leader or follow the regularized leader, online subgradient descent, right? Now, some of these are approximations, right? Incremental SGD and online subgradient descent are approximations, so they might not be good for different types of loss functions. Depending on what kind of gradient that loss function has, they might not be appropriate as approximations, but they are worth trying alongside your batch model in production, because if they are at least as good as that batch model, then probably you should select that model, right? What's the criteria for model selection? The simplest, most predictive model. And if an online model is as predictive as a batch model, I might say that in the context of the bias variance trade-off, it is simpler because it can be applied in a stream, right? Other things, maximum entropy using surprisal rather than a logistic regression, streaming k-means or canopy clustering if you're doing unsupervised learning, and then your research will have to vary from there depending on what you're looking at. Online gradient boosting, right? Cursive dimensionality models like tree-based models are going to suffer a little bit. But if you have a good boosting function, those boosting functions can be online, which essentially means that you just kind of train another tree at each step and then stick that one in and chop one of the trees off. And you're probably doing stumps anyway. So, okay, I won't get into that. I hear the chuckles. I won't get into that, but there are online forms of these algorithms that you can certainly try. While we're here, the idea of probability should become more important to us, and not probability that's smoothed or regularized using softmax. So it might be time to dust off some of our other old probability algorithms, in particular something like multi-armed bandits, right? Multi-armed bandits are fascinating because you can define a custom cost function or a custom reward function that really fits your application. And the learning process is an exploration versus exploitation learning process, right? How long are you going to stick in one area of the log before changing? And these systems are adaptive, right? Because they change with respect to real world conditions. And of course, more generally, I'm talking about reinforcement learning here. So reinforcement learning is another type of machine learning that works very well in a streaming use case, right? And bringing these ideas away from video games and robotics and digital agents into our analytics is a real boost that we can use in the sort of streaming versus batch capability. So real quick, I'm just going to quickly do a time check. The definition here is a digital agent that operates in a data-driven environment that makes decisions that maximize a reward function. And of course, there are a host of these things. Typically, when you guys research reinforcement learning, you're going to find two categories: policy gradients, which is like figuring out the gradient of whatever cost function or reward function you've come up with, and Q-learning, which uses Q tables. But there are other ones, Markov processes and Markov chains being the big one that have had or been very influential in the streaming community. Okay, but there's one sort of critical point here. There is no median, right? I told you how to compute an online mean, variance, standard deviation, minimum and maximum, but some algorithms just can't be converted to a streaming or online function. Median is a good example of something that you cannot compute without having the whole batch. You got to sort and you got to find the middle, and you can't sort if you don't have all of the data at your disposal. This is a little bit of a joke because there are definitely median approximation algorithms that you can do online. But I use there is no median as a reminder that sometimes you will have to deal with approximations rather than rigid optimizations of convex functions. And that's a little bit of a change of mindset that we have to have, right? Another example of this is incremental stochastic gradient descent, right? It actually doesn't have the same no free lunch properties as regular gradient descent has. In particular, it will definitely terminate property. So, you guys are laughing, right? There's a little bit of thought that you have to do into these tools that you're using when you're using them in real life in production. But frankly, getting that 87% number down and getting more models into production is probably worth the approximation. So this is my caveat. Just remember, there is no median, right? That doesn't exist anymore. You can get a mean, you can get a variance. There's no quantiles, there's no median. All right, on to the last topic here. This is more, there's a couple of data engineers in the room, and this is actually very exciting for me, this idea of data quality and deduplication in particular, and what is it that your database is doing for you anyway, right? I've been kind of negging on the databases here, which are great tools, and you should absolutely use them. But they're older, right? We need adaptations. We need new technology. And I think that in the data quality and deduplication and anomaly detection space, there's a lot of opportunity for work that our databases could be doing for us. So here is kind of my issue, right? The whole MLOps community has spun out a whole new system of databases for us as data scientists. Vector databases, model registries, feature stores. You may recognize these logos. There are thousands of these logos. My first slide was just covered in logos of all of these new vector database model registry systems that are out there for developers. But it really makes me ask the question, are these MLOps databases focusing on the right problem? They're focusing on model management, but does that mean that data management is a solved problem? Thank you for shaking your head so vigorously. I appreciate that. In the 20 years that I've been doing this, I can tell you from hard-won experience that data provenance, data quality, and data diversity are far better indicators of model success in the real world than any F1 score or RMSE or CEO marketing speech that I could possibly give, right? Our databases need to be doing this work for us. So I'm excited to announce tonight that Ensign is one of the first databases in the world to provide deduplication as a guaranteed service on top of these real-time streams. And I will caveat that in a little bit with some other databases that are doing kind of similar things. But we actually just released Ensign v12 on Sunday, and Ensign v12 shipped with deduplication. So figured we'd talk about it tonight. So if we have this ordered sequence of events, right? These events are simple datagrams, right? They can be anything. Ensign, Kafka, other systems of this type can be operated in a typed mode with a schema or in an untyped mode without a schema, right? So they kind of combine the best world of schemaless and schema-oriented databases at the cost of a little increased query time in order to do that parsing in real time as opposed to having the fixed parsing. So if we look at the stream, and let's say these two purple events are duplicates of each other, and these three orange events are duplicates of each other, shouldn't we be able to detect that in real time? Well, I just told you we have to think about algorithms that work in streaming fashion. And so the way that we did is by using Bloom filters. Bloom filters are a space-efficient probabilistic structure that use a series of hashing algorithms to do set determination. Is something in a set or is it not in a set? And it's probabilistic because there's the chance of a false positive, but there's no chance of false negatives. So what we do is in real time, we check if an instance is a member of this Bloom filter. And if it is, then we are guaranteed the possibility of a duplicate, right? And then we can use a hash table lookup to say, okay, well, what is the thing that that Bloom filter thinks that we're deduplicating or that we're duplicating? And then we can run through a structured comparison to see if it's actually duplicated or not. And in real time, using these algorithms, we can say, oh, that's a duplicate or that's not a duplicate. And this makes so many things easier, right? Think about your data ingestion. You're probably polling an API every 5 minutes. Okay, sorry, Siri. You're probably polling an API every 5-10 minutes for data, and it's probably giving you results back. You might have e-tags, you might have last modified, maybe some type of caching, but you might have to be doing the work of deduplication, right? And my question is, why should I tell you need to create a Bloom filter and a hashing function, all this stuff? The database should be doing that, right? And I firmly believe the database should be doing that, and Ensign is doing that on your behalf. Now, we should all ask ourselves as data scientists, okay, well, actually, what does it mean to be a duplicate, right? Entity resolution, canonicalization, these are hard things. So actually, we have a few different definitions of duplication that you can set inside of Ensign, and we think that this will become more prominent in other data systems as well. So of course, there's the strict definition, right? Metadata, data, MIME type, and type are all identical, right? The provenance may differ, the compression and encryption may differ. By the way, Ensign is a fully encrypted database, so your data is private and kept safe. Usually identical data does imply the same type and MIME type, right? It'd be pretty unusual for like Parquet to match JSON. I don't think that would really happen. So that's a strict definition. And so that might be the most important definition for you. But you might want to relax those things so that you can inject metadata into this sequence of events that you might have canonicalization processes or other entity resolution processes that you might add as metadata, as key value pairs on top of these things. So, if the typing information isn't important, you can just do data cram, right? Just the data has to match. Don't worry about the metadata. If you are adding things into the metadata that are important, you can do key grouped, right? So something has to be unique for a set of keys that have the same values. And then you can extend that idea onto unique keys, unique fields, and of course, no deduplication whatsoever. Now, the interesting thing about what Ensign does is it does deduplication in a completely lossless way. Again, with some caveats there. You can make it lossless if you care more about data storage, but you can switch from strict to datagram to key grouped and not lose any data inside of an Ensign system. Instead, Ensign tries to remove whatever duplicated data it can to save you space, but keeps whatever it needs to keep in order to change your deduplication policy or get those duplicates back if you want them. So it's a completely lossless prospect because, again, you have to have that reproducibility, right? Maybe you had a strict policy at one time you built your model and then you switched over to a key grouped policy. You need to have that reproducibility. You need to go back. So this doesn't throw away anything. It keeps what it can keep and it rebuilds the data when it can. Now, I mentioned before that, this isn't the only place that we can do data quality assurance. We can also start to do things like anomaly detection, right? There are several online algorithms for anomaly detection that work in similar ways, things like ecliptic envelopes, local outlier factor, one-class SVMs using those convex optimizations that I talked about before. Those are all very good methods for doing anomaly detection inside your data set. And so again, it begs the question, why isn't your database doing this for you, right? And in this place, this anomaly detection is coming soon to Ensign. You might look for that in 15 or 16 coming up soon. But, we're not the only ones in this space. And so, I'll just say that anomaly detection is already being embedded into other real-time systems, Red Panda being the one that's got that going right now with B something. Sorry, I've completely had a brain fart about the partner that they're working with. bhex, bgram.io, something like that. They have anomaly detection built in. But it's something we're working toward. And we are constantly asking ourselves the question, what should your data storage system be doing for databases, for data scientists, so that you can focus more on getting models to production, getting the value from those insights, and not worrying about the data engineering aspects of things, right? That's our goal. And hopefully I've convinced you that, thinking about real-time streaming is a good way for you to get those models to production as well. So that's it for me. I'm happy to take questions. I know I'm right at the end of my time here. So I'll defer to Janet and Jeff about, thank you. So yeah, if anyone has any questions or otherwise I can talk to you guys at the Yard House.
There's no medium. I mean, in some ways, we're already sort of tolerating approximations now in the big data space. In terms of like the training data, there's some calculations where you have to make approximations. And so I think we're sort of already doing it. So it's not really a new thing. And I think it's kind of time for it to accept that approximations are probably like what we should be kind of that approximations are okay and acceptable.
If you could go back to the slide that shows the different online algorithms. Yes. So I guess, my question is, can I find these in scikit-learn? Like where do I go to find some of these? Somewhere that is, something that's implemented, even if it's just a few of these, what are some suggestions you have so that I can start playing with some of these on my laptop?
Great question. Many of these are in scikit-learn, but I think the library to look at would be River, and the River machine learning library for streaming algorithms. Monte Carlo algorithms, also good candidate for streaming and doing streaming stuff. So maybe we'll see integration with PyMC and other things as well. Yes, please.
So data scientists, so you might have obvious answer to the question, but so you said when you showed us the first slide, there was like future engineering be part of the machine learning, and when you stream data, what does that mean for future engineering? Does that restrict the future engineering? Well, first of all, you said not every algorithm is transferable to online, right? So some subset can be used, some use cases. I guess what I'm trying to get is what is like from pragmatic perspective, what is the real use cases in like what does it solve in the real world, right? Because a lot of businesses really don't need real time data at all for data decision making, right? And this is solving like subset of those problems, which is not perhaps the majority of the use cases. And within specific of feature engineering, what are the implications? Like, does that mean that I can, if you look at the universe of machine learning problems, does that really limit me to very specific subset, or it's not really that much restricting?
It does. Yeah, I mean, it's switching to a real-time method of thinking is a state of mind, right? And so the idea that businesses don't need real time, I would question first off, right? Time to value is important to every organization and every business. Time to decision is important to every business. And it's not about the speed of computation. It's also to the speed of model realization and model deployment, the speed of collaboration. So the advantages that these systems are giving you isn't just, I can get you a decision very quickly. It's, I can give you a sequence of events and a provenance of events that is immutable, that I can always use for reproducibility and explanation, and I can fork off into other data streams, right? That ordering is what matters more than the real instance of time that thing appears, right? I mentioned before, time isn't real, when it comes to these databases. But to get to your question specifically about feature engineering, feature engineering normally finds itself in a pipeline form, right? And so what you'll be faced with these types of situations is how much do you want to do at every step of the pipeline, right? So, you have raw data would come into one topic, and then you would probably do some feature engineering on that raw data, and then you would push that into another topic. And so how much of that, and then you have another step and then another step, and now you have a feature engineering pipeline. And so the question is, where am I going to fork this pipeline so that I can do other types of feature analysis and model engineering, right? So you might do standardization, normalization, imputation. You might just do that all in one step because you're not going to fork that type of work, right? But if you're putting together a dictionary for, vector space, you'll probably have a fork of those dictionaries, because you're going to have different sets of corpuses or corpora that need to have different types of dictionaries or different types of vector spaces. So you're preserving a lot of pre-work, right, in the feature extraction pipeline, and then giving yourself the ability to read back instances at a previous step and do something different and get a new modeling outcome that's just as reproducible as the first. Yes, please.
New techniques that I'm hearing folks I work with and talk about a lot are, in terms of real-time kind of activities, is retrieval augmented generation. You know, database interfaces with large language models so that for example, internal corporate users can get a prompt kind of response. So there's that. And there's also federated AI learning, which is, you know, the push-pull of the actual algorithm rather than the data. Where does all this fit in that kind of new emerging constellation thing?
That's a very interesting question. Let's start with the federated training. TensorFlow uses Kafka under the hood. So already sequence graphs are being communicated using this model, and different batches or epochs will be entirely held within the same epoch, right? So, or within the same topic. So you have topic-based epochs already in TensorFlow. TensorFlow considers those epochs transient, so the topics don't have to be persistent. So one difference with what we're talking about here, rather than something like Kafka, is full persistence. Full persistence might get to the other thing that you were talking about extracting prompts from databases. Harlan Harris, who's a member of this community, has recently been talking about the cognitive behaviors of LLMs and whether cognitive disassociation can happen inside of an LLM. And I argue that yes, it can, right? Models that are trained on lots and lots of different user input can become too generalized or too split-brained. So instead, you want to have generative models that are scoped down, probably bigger than human sort of organizations, you know, more than 150 users, but probably something less than 1,000 or less than 5,000 users. And so inside of your systems, we really want persistence of the prompts that are coming through those LLMs inside of these topics, so that you can have a multi-AI system that doesn't suffer from that, you know, cognitive disassociation that you would see in other large AIs. Sure. Last question.
I don't ask. Model reproducibility. You have this immutable event stream. For compliance purposes, you have to be able to effectively at some point put on a tombstone record or something where you say, new event, this whole event can't be used for analysis or training. But when that happened, you trained a model previously on the event before it became non-usable. Does that impact reproducibility? Is the immutable event log actually still mutable?
Yeah, that's an important question. We can answer that in a technical sense. There's also a legal sense that we have to answer that in. So first part is the question of how anonymous a vector point is or is not, right? So it might be enough that you cannot reverse that vector point into some sort of user profile, right? That might be sufficient. If it's not sufficient, then you'll have to do something like put that instance into the middle of, you know, whatever vector space it's in. And, you know, you'll know that you've normalized that instance into some aggregate, right? but hopefully that point didn't have enough variance that it would really affect your model. And in the worst case, you would now know pretty quickly that that model is no longer reproducible. And so that's the worst case is, okay, time has gone on, enough users have deleted this data that this is not a usable model. And that probably will tell you something about your future value proposition for the models that you're training if users keep deleting that data.
Just kind of following on that, like, model reproducibility is important, but I would imagine in a case like this where they're saying you don't want this data anymore, then you really probably shouldn't be kind of going back anyway, scratching any kind of model trained on that data that you needed to do it. So
I'm hopeful that anonymization, differential privacy tools like that will give us the out that we need. But of course, that's up to the lawyers more than the technical side of things.
I add one more thing. And I think kind of along those lines, like we were talking about, like offloading some of the data from these external databases. Like the other thing that we can do is like mask data and things like that. So even though we can still kind of make the data usable for machine learning models, but protect privacy and make sure that we're securing the top concerns.
The database should also be doing hashing for you for your hash vector spaces.
Last one. How much more does this cost from an organizational perspective? Well, it means, like, from our perspective, do we be as data scientists and practitioners, are we going to get paid a lot more if we're going to do all this? Or does that mean that we're also taking on the additional engineering and DevOps responsibility that we wanted to avoid in the first place? So from an individual perspective and organizational total cost of ownership perspective, this looks like a great way to get more models into production, but what's the additional cost?
Storage costs go up because there's more more persistent data, more transformed data being stored around. It's all compressed, it's all encrypted, and it's not in S3 anymore, right? So it's on an SSD so that you can query it, which I would argue is far better than Athena. So your storage costs are going to go up. Your instance costs are going to go down because now serverless Lambdas become much more viable opportunity, and you're not thinking about those big GPU clusters anymore because we're not doing batching. So I would say that because instance costs are so much more expensive than storage costs, that overall you're going to see a cost reduction if you buy into this model. And I definitely hope that you'll get paid more for going this route. Yeah, but in terms of recourse constraints, storage goes up, compute goes down, network goes up.
All right, thank you all, and we will be leaving momentarily. Take some action out of with you for yourselves. No one wants to carry that on.
Can I just say one last thing real quick? Sorry. So I'm going to go to the Yard House. I'd love to meet all of you and talk to you. Prima, Rebecca, Edwin here. We have stickers. We'd love to get your business cards. We're going to be in DC. So if you guys would like to talk to us about your specific problems, we're going to be holding some office hours tomorrow and Thursday morning. So if you want to chat about what you guys are doing in your organization, about your job search, we'd be happy to talk to you, Wednesday or Thursday morning. And please do check out Ensign and our data playground and give us any feedback that you might have. Thanks, everyone.